Hi, physical science students. This is Mrs. Lewis, and we are back in our books with section 3, and now we're going to be using Newton's laws. So we're going to put them into practice. And as I look at this picture here, there's a couple of things that I'm thinking of. And the first is to tell you there is no up or down in orbit. So if not secured, objects simply float here and there. So spacewalks, like the one pictured here, are termed EVAs, and that stands for extra vehicular activity. So the purpose of this section and using Newton's laws is 1. On Earth, how can you tell up from down? And 2, if a scale floated by and an astronaut stood on it, what would the scale say? Newton's first law of motion can explain what happens in a car crash. When the car abruptly stops, the passengers will continue to move unless acted on by an outside force. This crash dummy was restrained safely with a safety belt and cushioned with an airbag in this low-speed crash. So therefore, safety belts and airbags can counteract the force of inertia in order to reduce injuries and save lives. Newton's second law and gravitational acceleration. When all forces except gravity acting on a falling object can be ignored, the object is said to be in a free fall. Please record these 3 bullet points. Close to Earth's surface, the acceleration of a falling object in free fall is about 9.8 meters per second squared. This acceleration is given the symbol g and is called acceleration due to gravity. If an object is in free fall near Earth's surface, the net force on it equals the force of gravity. F net equals F gravity. So continuing in your notes, you can use Newton's second law to show that for an object in free fall, its acceleration due to gravity is equal to g. Next, subtitle, air resistance. Is a friction-like force called air resistance opposes the motion of objects that move through the air. Okay, so what does that mean? It means just this. These 2 bullet points should go in your notes. The amount of air resistance on an object depends on the speed, size, and shape of an object. Air resistant, not the object's mass, is why feathers, leaves, and pieces of paper fall more slowly than pennies, acorns, and apples. In a vacuum, there is no air resistance. As a result, a feather and a billiard ball, like you would find on a pool table, can fall with the same acceleration in a vacuum. On August 7, 1971, during the Apollo 15 mission, astronaut David Scott conducted an experiment.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
So that leads us into terminal velocity. Please write it down. Is the highest speed a falling object will reach. The terminal velocity will depend on not only the size, but the shape and the mass of a falling object. So as an object falls, the downward force of gravity, as you learned earlier, is going to cause the object to accelerate. As an object falls faster, the upward force, the force that moves this way, of air resistance increases. And this causes the net force on a skydiver to decrease as the skydiver falls. Finally, the upward air resistance force becomes large enough to balance the downward force of gravity. This means the net force on the object is 0. then the acceleration of the object is also 0, and the object falls with a constant speed called the terminal velocity.
Drag force and terminal velocity. If you drop a table tennis ball, as shown above, it has very little velocity at the start, and thus only a small drag force. The downward force of gravity is much stronger than the upward drag force, so there is a downward acceleration. As the ball's velocity increases, so does the drag force. Soon, the drag force equals the force of gravity. When this happens, there is no net force, and so there is no acceleration.
Your new heading will be free fall. Okay, and so let's talk about free falling and weightlessness. So you've probably seen pictures of astronauts and equipment floating inside the International Space Station. And if you haven't, we're definitely going to be watching some videos of the International Space Station later on in the year. They are said to be experiencing the sensation of weightlessness. So according to the law, right here, write this down. According to the law of universal gravitation, at 400 kilometers altitude, the force of Earth's gravity is about 90% as strong as it is at Earth's surface. So an astronaut with the mass of 800 kilograms still would weigh about 700 newtons in orbit, compared with the weight of about 780 newtons at Earth's surface. The astronaut is not weightless.
What do you think is weight? Because the weight force is defined as Fg equals mg, Fg changes when g varies. On or near the surface of Earth, g is approximately constant, so an object's weight does not change appreciably as it moves around near Earth's surface. What happens if you stand on a scale in an elevator? As long as the elevator is in equilibrium, which means the net force acting on it is 0, the scale will read your weight. What would the scale read if the elevator accelerates upward? You are the system, and upward is the positive direction. Because the acceleration of the system is upward, the upward force of the scale must be greater than the downward force of your weight. Therefore, the scale reading is greater than your weight. If you ride in an elevator like this, you would feel heavier because the floor would press harder on your feet. On the other hand, if the acceleration is downward, then you would feel lighter, and the scale would have a lower reading. The force exerted by the scale is called the apparent weight. An object's apparent weight is the force an object experiences as a result of all the forces acting on it, giving the object acceleration. Imagine that the cable holding the elevator breaks. What would the scale read then? The scale and you would both accelerate with A is equal to minus G. According to this formula, the scale would read 0, and your apparent weight would be 0. That is, you would be weightless. However, weightlessness does not mean that an object's weight is actually 0. Rather, it means that there are no contact forces pushing up on the object, and the object's apparent weight is 0.
So, just for an example, to have a conversation, if a spacecraft in orbit is in free fall, but it is falling around Earth rather than straight downward, everything in the orbiting spacecraft is falling around Earth at the same rate. In the same way, you and the scale were falling in the elevator. Objects in the spacecraft seem to be floating because they are all falling within the same acceleration. So if I were you, I would not redraw that diagram, but yet you could refer to the horse diagram, quote unquote, that you did in the last chapter. So our next tagline is Centripetal Force, and you need to write underneath that, it means the net force exerted toward the center of a curved path. That means anything that moves in a circle is doing so because a centripetal force is accelerating it towards the center. So there's that word traction again. So when a car rounds a curve on a highway, a centripetal force must be acting on the car to keep it moving in a curved path. This centripetal force is the frictional force or the traction between the tires and the road surface. So just imagine for a moment that you're whirling an object tied to a string above your head. The string exerts a centripetal force on the object that keeps it moving in a circular path. In the same way, Earth's gravity exerts a centripetal force on the moon that keeps it moving in a nearly circular orbit. So recall that acceleration is the difference between the initial and final velocity. So write that down. Acceleration is the difference, it's the subtraction between initial and final velocity, thus divided by time. It's also Newton's second law. The net force of an object equals its mass times its acceleration. So combining these two relationships, Newton's second law can be written in this way. Next subject line, law of conservation of momentum. It states that if no external force acts on a group of objects, their total momentum doesn't change. That is, momentum is conserved. The momentum of an object doesn't change unless its mass, velocity, or both of those things change. Momentum, however, can be transferred from one object to another. Momentum is conserved in collisions with more than two objects if there are no external forces acting on those objects. So the momentum of the cue ball just before the collision is equal to the total of the momentums of the billiard balls, including the cue ball, just after collision. The balls scatter left and right as they are deflected by the cue ball. Momentum is conserved separately in each direction, and the sum of the forward velocities of the balls equals the cue ball's initial velocity. The sum of the left velocities is equal to the sum of the right velocities. So, why do the balls eventually slow and stop? Can you answer? That's right, friction. I hope now that you can answer those two questions on how can you tell up from down while on Earth, and if a scale floated by and an astronaut stood on it, what would the scale say? This concludes Chapter 3.